So, last time we finished chapter 20. The chapter 19 homework is due on the 30th. The chapter 20 homework is due on the 4th. We're going to start chapter 21. Chapter 21 homework is in two parts. The first part is due on the 11th. So we're running a little ahead of schedule, and that's a good thing. Any questions about stuff from Monday, or you're already okay? So continuing on, starting up chapter 21, we're going to start talking about circuits. So finally, we're going to cover material that matches our labs. So we're going to talk about electric current and direct current circuits. So we've talked about static electricity. Now we're going to talk about moving electricity. And here we have a circuit. We have two bulbs in series, and then here we have a setup with two bulbs in parallel connected to one bulb in series, forming a circuit. So we're going to discuss electric current. That's the movement of electricity, resistance, and Ohm's law. So most things have a resistance. They resist the flow of electricity. That resistance for many objects can be described with Ohm's law. Energy and power in electric circuits. So we'll talk about energy and power. Then we'll talk about what happens when we have resistors, which are, resistive elements, either in series or in parallel. And once we've discussed that, we'll go on to Kirchhoff's rules for how to work out circuits more in general. Then we'll discuss capacitors, circuits with capacitors, how capacitors act in direct current circuits, how capacitors act in series and parallel. We'll look at RC circuits, circuits with a resistor and a capacitor. And then lastly, we'll talk about ammeters and voltmeters. And we will use them in lab starting today. So we have a lab today. Our first lab will actually be about things in series in a circuit. So simple circuits that are in series, we'll be measuring current in that. So electric current is the flow of electric charge from one place to another. And electric current is measured in units of amperes. And 1 ampere is 1 coulomb per second. So current is defined as delta Q over delta T. It's the rate of flow of charge. It's a coulomb, and the unit for current is a coulomb per second. The symbol is a capital I. And a closed path where charge can flow, returning to its starting point, is called an electric circuit. Because it's like a circuit, it's a circular loop. And for current to flow continuously, you need a closed circuit. It needs to go from, say, the positive side of the battery to the negative side of the battery through some circuit. So a battery is a device that uses chemical reactions to produce a potential difference between its terminals, usually some sort of redox reaction. It causes current to flow through a flashlight bulb. So here, if you have a battery hooked up to a bulb, flow through a flashlight bulb, similar to the way a person lifting up water causes the water to flow through a paddle wheel. In our labs, we've been using power supplies that take the AC current from the walls, which is generated far away, and turns it into DC current. But that's the general idea. Battery is a device that generates a potential difference with a chemical reaction. And a battery that's disconnected from any circuit will have an electric potential difference between its terminals. That's called the electromotive force, or EMF. So any random battery, I have batteries over here. So if I have like a Radio Shack battery, I can measure the voltage between its terminals. And that voltage so this battery has an EMF of 9 volts. Okay, so this is a pretty dead battery, it's at 8.61. This is a random potentially dead battery. So if I get like a brand new battery, and measure the voltage between the terminals. Yeah, it's a little bit more. Well, that other one was pretty flat. But if you have a battery has two sides, and it will have some potential difference between the terminals, which is formally called the battery's EMF and practically called the battery's voltage. Everybody just calls it voltage. And it stands for electromotive force. Despite its name, it's an electric potential and not a force. It's a terrible name. It's one of those historical names. The amount of work it takes to move a charge from one terminal to the other is the charge, delta Q, times the electromotive force. So battery can move so much charge. Now, current, the direction of current flow that we talk about is the direction that positive charges would flow in a circuit. So the direction of current flow for circuits and the charges of what's positive and what's negative was decided before we knew that the actual thing that was moving was electrons. And then the electrons are negatively charged. Therefore, current flows around a circuit in the direction of a positive charge would move, while the actual moving particles are moving in the opposite direction. Because history. Benjamin Franklin's fault, actually, if I remember correctly. I could be wrong. I might be. He did name the electrons. I don't remember if he was the one who set the charges, positive and negative. But what was positive and what was negative was determined well before we knew what was actually moving. So current will flow around the circuit in the direction of positive charge while electrons are actually moving the other way. Now, most of the time, this doesn't matter because you're not looking at the electrons. It's relevant in a few cases when you think about stuff like the design of stuff like vacuum tubes that are used in actual electron, jumping a gap. So when you design a vacuum tube, your negative terminal is a thin line and your positive terminal is a big target kind of thing. Sometimes the direction matters. The actual direction of what's moving matters, but usually it doesn't. I don't think it will matter in any of the lab. The vast majority of circuits, it doesn't really matter. So the actual movement of electrons along a wire is not very fast. What we're looking at is sort of the average flow. Electrons spend most of their time bouncing around randomly and have only a relatively small velocity component opposite the direction of the current. But the signal propagates much faster. Electric signals propagate at something like a good fraction of the speed of light, like a third or something like that. They're very fast. But the electrons in question don't necessarily move anywhere near that fast. They just push on the next electrons down the wire, kind of thing. So current is sort of the rate of electrons moving, but there's a lot of electrons. So they don't necessarily have to move very fast. So here, batteries are rated in milliamp hours. Modern batteries. So if you have a cell phone battery that's rated at 2600 milliamp hours, how many electrons can that provide a phone? Remembering that an amp is 1 coulomb per second, and that an electron is 1.60 times 10 to the minus 19 coulombs. So I'll give you a few minutes to work on this and try and work it out. So this is basically a question about unit conversions. So the first step is to convert milliamp hours to coulombs, because milliamp hours is a current times the time, that's a charge. So 2600 milliamp hours, that's 1 amp per 1000 milliamps times 3600 seconds per hour. You basically end up multiplying by 3.6 to get 9,360 coulombs. So our charge is 9,360 coulombs, and then we want to figure out how many electrons that is. Well, the number of electrons is the charge divided by the charge of an electron. So 9,360 coulombs divided by 1.6 times 10 to the minus 19 coulombs gives us 5.85 times 10 to the 22 electrons. So a battery that's rated at 2600 milliamp hours can provide a phone a total of 5.85 times 10 to the 22 electrons. Now, a battery with an EMF or a voltage of 1.5 volts delivers a current of 0.42 amps to a flashlight bulb for a time of 77 seconds. So first, we want to find the charge that passes through the bulb, and then second, we want to find the work done by the battery. So the work done by a battery is going to be, delta charge times EMF. or EMF. Right. So I'll give you a little while to work on this one as well. So first we want to find the charge that passes through the bulb. Well, because current is delta Q over delta T is going to be I times delta T. Our current is 0.42 amps. Our time, delta T, is 77 seconds. The 0.42 amps times 77 seconds gives us a delta Q of 32.34 coulombs. We want to find the work done by the battery as well. So we would round this to 32 coulombs because I'm choosing the The work is going to be the charge times the EMF, delta Q times the EMF. So 32.34 coulombs times 1.5 volts is 48.51 joules or 49 joules. Fairly straightforward. So let's rate the work done by these batteries from highest to lowest. So we have 4 batteries, various voltages. Battery A is 3 volts, battery B is 9 volts, battery C is 12 volts, battery D is 15 volts. They're running at various currents. Battery A is running at 1 amp, B is 2 amps, C is 5 amps, D is 10 amps. And they're running for various times. A is running for 40 seconds, B is running for 10 seconds, C is running for 2 seconds, and D is running for 1 second. So remember, delta Q is current times time, work is current times EMF. So we want to rank these batteries in work done from highest to lowest. Which is fine. I don't care what we're doing. So from now on, very good. Thank you. So we can go through these. Let's start with system A, battery A. Well, battery A, so the general formula here is that, delta Q is I times delta T. Work is Q times EMF. So to get the work, you end up just multiplying all three of these together. Work is EMF times current times time. So the work for our A is 3 volts times 1 amp times 40 seconds. A helpful thing that will come up again later is that voltage times amperage is power. So 3 volts times 1 amp times 40 seconds gives us a work of 120 joules. So A is 120 joules. B, 9 volts times 2 amps times 10 seconds. That gives us 180 joules. B is 180 joules. C, 12 volts times 5 amps times 2 seconds. That also gives us 120 joules. And D, 15 volts times 10 amps times 1 second gives us 150 joules. So I didn't put this in here, but from greatest to smallest, B is biggest, then D, and then A and C are equal at the smallest. So the summary is that B is greater than D, which is greater than A, which is equal to C. Actually, let me put that on the slide, and then I'll update the slides. There we go. So we talked about current and work. Now, under normal circumstances, wires present some sort of resistance to the motion of electrons. It takes a certain, they're pushing back against the flow of electrons. And for most materials or most things, follow what's called Ohm's law. So Ohm's law relates voltage to current via this concept of resistance. However, the thing about Ohm's law is not universal. It only applies to most materials, but it only applies to certain materials. Most metallic conductors are ohmic, they follow Ohm's law. Other thing, if you have a resistor, a device that is a resistor, it will follow Ohm's law because it's designed to do that. But there are things out there that don't follow Ohm's law. Materials that don't follow Ohm's law, like the voltage current relationship, for example, for a light emitting diode looks nothing like Ohm's law. But the voltage current relationship for a light bulb generally looks something like Ohm's law. So there can be effects from temperature, so that can be a fact. So Ohm's law is that voltage equals current times resistance. The voltage required for some current, now, so if you have a current, some current passing through something with a known resistance, R, that the current times the resistance gives you the voltage required to get that current flowing. So if we solve for resistance, we find resistance is voltage over current. And the units of resistance, volts per ampere, are called ohms. What is the Okay, I'll fix that. It's another thing. So the unit of resistance is ohms, and it's 1 volt per amp. Not that. So and the symbol for ohms is a capital omega. It looks like a horseshoe. Because we're getting into electrical symbols where they started running out of letters. But the unit for ohms, it's expressed with a capital omega. And it's called an ohm because it was discovered by Ohm, Friedrich Ohm. Hence Ohm's law. So if a potential difference of 12 volts is applied to a 250 ohm resistor, what is the current? So this is fairly straightforward. Voltage equals current times resistance. The current is voltage divided by resistance. 12 volts divided by 250 ohms gives you 0.048 amps. Or 48 milliamps. So 150 ohm resistor carries a current of 0.026 amps. What is the voltage across that resistor? Well, this is also fairly straightforward. Voltage is current times resistance. So 0.026 amps times 150 ohms gives you 3.9 volts. And then if the voltage and the resistance are doubled in a simple battery resistor circuit, how will the current change? So what do you think will happen if I double both the voltage and the resistance? Well, let's think about it. Voltage equals current times resistance. So current is voltage over resistance. So if I double both the voltage and the resistance, the current one is voltage over resistance. Current 2 is going to be 2V over 2R. The 2's will cancel. You'll just have V over R, which is the same as current 1. If you double both the voltage and the resistance, the current doesn't change. Now, that's basically setting up. So that would be, you put two resistors and 2 batteries in your circuit to double it up. And the current would stay the same. Now, if you double the voltage without changing the resistance, the current does double. Now, if you have 2 wires of the same length and diameter, they'll have different resistances if they're made of different materials. Different materials conduct electricity at different rates. This is a property of the material. It's called the resistivity. There's one over the property of material called the conductance. So some materials are excellent conductors, like silver. Silver is one of the best conductors out there. Some materials are terrible conductors, like wood. But if you have some material, it will have a resistivity. And then if you know the resistivity of a material, you can work out what the resistance of a wire made of that material will be. So the resistance of a wire, in terms of the resistivity rho, you want to work out what the resistance of a wire is. Resistance is the length of the wire over the cross-sectional area of the wire times the resistivity. And the units of resistivity are in ohm meters. So the general idea is that if you increase the length of a wire, the resistance goes up. It's got to go through more wire. That makes sense? But if you increase the cross-sectional area of a wire, it's like making a pipe wider. And so the resistance goes down because there's more ways the electricity can travel. There's more room for the electricity to travel the distance. So it turns out the resistance is the length over the area times the resistivity, which is a property of the material. So if you have a wire and you know its length and you know its area and you know the resistivity, you can work out the resistance. Now, the difference between insulators, semiconductors, and conductors can be seen in their resistivity. So some examples of insulators. The resistivity of quartz in ohm meters is 7.5 times 10 to the 17. Rubber is 1 to 100 times 10 to the 13 ohm meters. Glass is 1 to 10,000 times 10 to the 9 ohm meters. There's a lot of variability in glass. And then semiconductors, you can see their resistivity is much smaller than this. 0.1 to 60, 0.001 to 0.5. And the other thing is that the resistivity of a semiconductor can be affected a lot by small variations in contaminating materials, like adding additional materials. The type and amount of impurities it contains. And this property makes them particularly useful in electronic applications because we can make them be right on the edge, or we can adjust them to have certain properties by adding or removing impurities. And we can also make them in such a situation that we can arrange the impurities in such a way that the addition or removal of an electric field will change whether or not it acts as a conductor or a resistor, basically making a switch out of it. So an electric switch, which is very useful. That's what a transistor does. A transistor is something where the amount of voltage you apply to one wire affects the resistance, the ability to flow through another wire. And then conductors have much smaller resistances. So lead is 22 times 10 to the minus 8. Resistivity. Iron is 9.71 times 10 to the minus 8. Tungsten is 5.6 times 10 to the minus 8. Aluminum is 2.65 times 10 to the minus 8. Gold is 2.2 times 10 to the minus 8. Copper is 1.68 times 10 to the minus 8. Annealed copper is 1.72 times 10 to the minus 8 because there's less discontinuity defects and such in it to get in the way, basically. And silver is 1.59 times 10 to the minus 8. That seems wrong. So what's a little bit less than I have to look it up again. So in general, the resistance of materials will go up as the temperature goes up due to thermal effects. So the higher the temperature, the higher the resistance. This property can be used in thermometers. So you can make a thermometer that's basically just a resistor, and you measure the resistance of that device to measure the temperature. I did that a lot when I was measuring things at very low temperature in my research. So the primary thermometers I used were resistance thermometers. And for semiconductors, the resistivity decreases with increasing temperature because of increased free electrons, but that has to do specifically with the way that semiconductors work. Semiconductors are, because they're sort of balanced on this edge. If you heat up, more electrons get kicked up to a higher energy level where they can conduct. And resistivity decreases as the temperature decreases, but there's a certain class of materials where resistivity will actually drop to 0. These are called superconductors. Resistivity will drop suddenly to 0 at a finite temperature called the critical temperature, T critical. And thus you can have a current flowing with 0 resistance. There is, however, a maximum current that can flow. That superconducting state will usually break down with a certain level of magnetic field, it turns out. Right? We're not going to go into any details on superconductors. They exist. They're incredibly useful. Generally, they need to be very cold. They come in several types. In traditional superconductors, there was a traditional superconductor on the list of stuff there. Lead is actually a superconductor down at liquid helium temperatures. But when people talk about superconductors, they're usually talking about high temperature superconductors, which, can work down at liquid nitrogen temperatures. So only cold enough to liquefy air. And those have a slightly different mechanism than traditional superconductors. They're called D-wave superconductors. But the resistance of a wire in terms of resistivity, the length and cross-sectional area of a wire is, if you know the resistivity, it's length times divided by cross-sectional area times the resistivity. So if wire 2 has twice the length and diameter of wire 1, if the resistance of wire 1 is R1, what is the resistance of wire 2? So wire 1 is length L and diameter D. Wire 2 is length 2L and diameter 2D. So if the resistance of wire 1 is R1, what will the resistance of wire 2 be in terms of R1? So here, resistance is length over area times the resistivity. Both of these wires have the same resistivity. So resistance 1 is length over pi times the radius, diameter over 2 squared times resistivity. So resistance 1 is going to be 4 length over pi d squared resistivity. Let's work out what resistance 2 is. Resistance 2 is going to be 2L over pi 2d over 2 squared times resistivity, which is going to be 2 times length over pi 2d squared rho, where if we substitute in R1, we'll find that resistance 2 is half of R1. Because, well, we doubled the length, which doubles the resistance. We quadrupled the area by doubling the diameter, and that quarters the resistance. So this wire will have half the resistance of this one. So here, a current of 1.97 amps flows through an annealed copper wire that's 2.25 meters long and 1.47 millimeters in diameter. And we want to find the potential difference between the ends of the wire. And the resistivity of annealed copper is 1.72 times 10 to the minus 8 ohm meters. So remember, resistance is the length of the wire divided by the cross-sectional area of the wire times the resistivity. And voltage is current times resistance. Also, the area of the circle is pi times the radius squared. So first, let's find the resistance of this wire. Resistance is length over cross-sectional area times resistivity. That's 2.25 meters over cross-sectional area, pi times 0.0147 meters over 2. Half the diameter is the radius squared, times 1.72 times 10 to the minus 8 ohm meters. That is 0.0228 ohms. Voltage, potential difference, is current times resistance. So that's 1.97 amps times 0.0228 ohms, which is 0.0449 volts. So 3 significant figures. So to find the resistance of a wire, you can use the resistivity formula, and then to find the voltage, you use Ohm's law. And most metals follow Ohm's law. I'll just keep going. So let's talk about energy and power in electric circuits. We talked a little bit about the work moving charge, but when a charge moves across a potential difference, its potential energy changes. Therefore, the power it takes to do this is the change in potential energy over the time, which is delta Q over V over delta T. But as we discussed, current is delta Q over delta T. So electrical power, which is just power, has units of watts, and power is current times voltage. So to figure out the power of something in watts, you just multiply the current times the voltage. So that's nice and straightforward. And when in materials where Ohm's law holds, because Ohm's law doesn't hold for all things. Most random materials, Ohm's law holds, but not everything. Power will equal current squared times resistance, or voltage squared over resistance. And in resistive materials, what that power becomes is primarily heat. And so you will have, for certain material things, you can have the resistance of something change with temperature. So for example, the resistance of a light bulb will change as it heats up. That's just because the resistance of the material is made of changes with temperature. The power mostly becomes heat inside the resistive material. Yeah. So if you have a fixed current, bigger resistance, more power. But if you have a fixed voltage, smaller resistance dumps more power because you get more current flow. Now, when the electric company sends you a bill, they do not send you a bill in units of joules. They send you a bill in units of kilowatt hours. They are charging you for energy units. And a kilowatt hour is a unit of energy. Much like for batteries, we have a unit of charge, which is amp hours or milliamp hours. For electricity, we have a unit of energy, which is kilowatt hours. 1 kilowatt hour is a kilowatt, 1,000 watts, times an hour, 3,600 seconds. So that is 3.6 times 10 to the 6 joules, or 3.6 megajoules. So a kilowatt hour is 3.6 million joules. And you can understand why maybe they charge things in kilowatt hours instead of joules. Also, for practical reasons, it was probably easier to measure kilowatt hours because you can make a device that, rotates depending on the current that's flowing through it and does so over time, and that ends up recording kilowatt hours. So if you have an electric motor runs on a 9-volt battery. If the motor is rated at 7.5 watts, what is the current supplied by the battery? So remember, power is current times voltage. We know the voltage, 9 volts. We know the power, 7.5 watts. We want to find the current. So power is current times voltage. That means current is going to be power divided by voltage. So 7.5 watts divided by 9 volts gives us 0.833 amps. So now we have a battery with a voltage V connected to a 5-watt light bulb. Later, the light bulb is replaced by a 10-watt light bulb. In which case does the battery supply more current? And which bulb has a higher resistance? So we have a voltage V battery connected to a 5-watt light bulb. Later, it's replaced by a 10-watt light bulb. When does the battery supply more current? And which bulb has a higher resistance? So power equals current times voltage. That means current is power over voltage. So the current for the 5-watt light bulb is 5 watts divided by V. The current for the 10-watt light bulb is 10 watts divided by V, which is 2 times the current for the 5-watt light bulb. So the 10-watt light bulb has the higher current. Current is voltage times resistance. The resistance is voltage over current. The resistance for the 5-watt light bulb is voltage over current 5. The resistance for the 10-watt light bulb is voltage over current 10. But we know that current 10 is 2 times current 5. The voltage over 2 times current 5 is half the resistance of 5. The higher power light bulb has a lower resistance. Basically, because voltage is constant, power is proportional to voltage squared over resistance. To get more power with the same voltage, you use a smaller resistance. And that puts out more power. So a battery with an EMF of 12 volts is connected to a 545 ohm resistor. How much energy is dissipated by that resistor in 65 seconds? Power is current times voltage. Voltage is current times resistance. The power ends up being voltage squared over resistance. So 12 volts squared over 545 ohms gives us a power of 0.264 watts. And the energy dissipated, delta E, is power times delta T. So 0.264 watts times 65 seconds is 17.2 joules. And the last thing we're going to do today, last question for today, is going to be a pizza is cooked in an oven in 15 minutes, assuming the oven draws 20 amps at 220 volts and uses electrical energy that costs, that is nice and cheap at $0.068 per kilowatt hour. How much energy does it cost to cook the pizza? So how much does it cost to cook the pizza? So what you need to do is figure out how many kilowatt hours is used to cook this pizza. And if it costs, and the electrical energy is 0.068 per kilowatt hour. And so you want to figure out how much that energy costs. I'm pretty sure I pay like twice that for my electrical bills. But I do live in the city. Yeah. And the book is old. And even given book is old, that's low. More than twice, but whatever. So power is current times voltage. So 20 amps times 220 volts is 4,400 watts, or 4.4 kilowatts. Energy is power times time. The time is 15 minutes. With 1 hour is 60 minutes, it's 0.25 hours. So 4.4 kilowatts times 0.25 hours is 1.1 kilowatt hours. And then 1.1 kilowatt hours. The other thing you could do is the time is 15 minutes is 900 seconds. 4,400 watts times 900 seconds is 3,960,000 joules. And then you can convert from joules to kilowatt hours, which would also give you 1.1 kilowatt hours. And then 1.1 kilowatt hours times 6.8 cents per kilowatt hour gives you a final cost of $0.0749. Or about 7.5 cents. And I'm going to stop there for today. So I'm going to stop sharing.